Hi everyone, Dr. B here. In this episode, I'm going to talk a little bit about shapes of distributions. Now, we just got done talking about graphs in recent presentations, and we're about to turn our attention to measures of central tendency and measures of variability, and then from there, inferential statistics. And more so than ever, visualizing what our concepts and visualizing our data are important things to be able to do. So we're all visual learners, and therefore I always like to emphasize how statistics is very visual. And a few things will get that point across more than referring to the shapes of distributions. Now again, distributions refer to how our data is distributed in our sample or in our populations, right? So there's an infinite number of ways that it can be distributed, and we're going to take a look at some of the common ones, okay? So the one that we're going to be spending an awful lot of time on are normal distributions like we have here. Now, I've already introduced normal distributions earlier, and I'm going to talk about them again now, and we're going to talk about them to death as the weeks go on. So we are going to really spend a lot of time looking at the normal distribution. That's a really big one in especially inferential statistics heading our way. So a couple of early concepts to get under our belt are the concepts of skew and kurtosis. These refer to how a normal distribution can be distorted from perfect, a nice perfect normal curve like we have on the screen here. That's a nice perfect normal curve. Now they can be distorted from that in two general ways that we describe here with big $5 words: skew and kurtosis. Okay, so let's take a look at those. Let's start with kurtosis. Kurtosis, it has to do with the amount of variability in the distribution, and it will affect the height and the width of the distribution. So another term for kurtosis is how peaked or peakedness, how much peakedness we have in the distribution. I think a perfectly good term is scrunchiness. How scrunchy is the distribution? Okay, so if I take a normal curve and pinch it together, if I scrunch it up, okay, in other words, make less variability, we'll go off in this direction in what we call another $10 word here, leptokurtic. All right, so we start with a mesokurtic normal distribution here, and if we tighten it up, in other words, if there's less variability, if there's fewer low scores and fewer high scores in whatever the variable is that we're looking at here, it will press this thing together and make it taller and skinnier. Now, I should point out that I'm making kind of theoretical interpretations about great big populations, a population of a set size, a set number of people in it, if you will. So think of these, I don't want to mix metaphors, but I will. Think of these as like water balloons, all right? They're kind of weird shaped water balloon laying on the floor or something, okay? Now, I'm not going to change the amount of water in the balloon. I'm not talking about changing the number of people in the sample or the population that we're referring to here. So if the population is closer together, if they're not as different, okay, if there's not as much variability in them, then we will have what's called a leptokurtic distribution compared to a possible mesokurtic. On the other hand, if there's more variability, then the water balloon kind of gets pulled out and lower, okay, and it becomes platykurtic. All right, how can you remember these things? Okay, I don't know. Platy. This is the same prefix in words like plateau. Flat, plate, flat. All right, platypus. It looks like the bill of a duck-billed platypus. All right. Meso means middle. A mezzanine is the middle floor between two floors. And lepto, think of leap. It's leaping upward, okay? I mentioned in the past I have a biology minor, and I like to be able to use that whenever I can. And so I can remember having to learn all kinds of genus, species, kingdom, family names for organisms. And I remember that. I remember so few of them. It's been so many years. But I remember, and I hope I'm right, that the rabbits belong to a class or order or genus, or I forget which category. They belong to something called the Lepidopteras. Okay, the Lepidoptera. Okay, lepto means to leap, like a rabbit. Okay, so it's leaping upward. Now, again, I want to make the point very clear that when you're describing how a population might, if you're talking about possible shifts in a population or comparing two or three possible populations, referring to how it might vary, the population size stays the same here in these pictures. Okay, so it's we have to have a conservation of mass, if you will. All right, so if we go from a normal distribution, for a normally distributed population to a leptokurtic population, those same people are going to be squished together like the water in that water balloon. And so it not only gets narrower, but taller and skinnier. Platykurtic refers to shorter and fatter. Okay? Does it make sense? Okay. So I call it scrunchiness. How scrunchy is the distribution? Some distributions are scrunchy. Okay? Now, take intelligence. We're going to talk a lot about intelligence this semester. So intelligence is thought to be is known to be normally distributed in the large population as a whole. All right? Now take a population like college students, okay? It's going to be a lot more scrunched up, okay? It's not going to be quite as spread as the regular distribution, okay? So anyway, when there's a medium amount of variability in a population, it's mesokurtic, and if it's a very tight, narrow distribution, we'll call it leptokurtic, and if it's spread all over the place and really a big range between low scores and high scores on something, it's said to be platykurtic. Okay, now there's no fine line where these things go from meso to lepto or platykurtic to meso. These aren't specific locations, okay? So we just refer to them as the extremes. Okay, so that's kurtosis, the amount of kurtosis. Now, there's mathematical calculations to express the degree of kurtosis in a distribution of numbers. We're not going to go there in this introductory level. We're going to see that sometimes in outputs. We might see it in SPSS. You see it on Microsoft Excel, statistical outputs of various kinds. So just know that that's possible, but that's beyond the scope of our course here. You can mathematically express the amount of kurtosis. Okay, so. All right, the other way that a normal distribution can vary, not just tall and skinny or short and fat, is if you kind of punched it in one side or the other and you made it skewed, all right? So here we have a couple of skewed distributions. And so they can be skewed in a positive or in a negative direction. So it becomes a non-symmetrical kind of thing here. So, normal curves are said to be symmetrical. When they're perfect, they're symmetrical. The left half is a mirror image of the right. So obviously a skewed distribution is going to be a violation from that. It's going to become, non-symmetrical. All right, so we refer to them as positive and negative, and these are not value judgments, okay? They're just which direction is the tail being pulled off into. And this might be a little bit counterintuitive. I found it a little bit counterintuitive as I was learning these. So on the left here we have a so-called positive distribution, and my example is going to be reaction time. Okay, so reaction time meaning slow on this end and fast on this end, and maybe how many people or what percentage of people respond, say, to a tone and press a key on a keyboard. Okay, we measure their reaction time in milliseconds, how quickly they respond. Now it's backed up against a wall here, hence it's skewed. You can't get, you can't respond quicker than 0 milliseconds. All right, if you respond too quickly, it doesn't count. So it's backed up against the wall here at 0 milliseconds here, but as you can, obviously there's no limit to how long you might fall asleep at the keyboard, and there's no limit to how long it might take somebody to press the keyboard. All right, so most people are going to respond kind of quick, so the peak, the highest part represents where most people fall. Most people are under this peak of quick reaction times, a relatively low number of milliseconds. And as we get older, we get slower. All right, as we get tired, we get slower. As we get more high, we get slower. Okay, all kinds of things can lead to slower reaction time. We get confused, we have slower reaction time. As we get overwhelmed, as we try to multitask, okay, all kinds of things lead to slow reaction times. Hence, reaction time is a very popular um, 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 having a brain fart here. It's a very common measure, dependent variable in research. Okay, so there we go. That's an example of a positive distribution. I'll come back in a moment as to talk about why I think this is sometimes a little bit counterintuitive. Let's get the other one out of the way first. So here's a negative distribution over here, and the example is the same one I was mentioning a moment ago. College student IQs not only are going to be a more compressed range of scores compared to the population, but it's going to even more characteristically cause a skew, a negative skew in the distribution. So again, in the whole population, intelligence is normally distributed, nice and equally normally distributed in the population, okay? Well, think about it. Colleges are going to be a lot less likely to accept, people are going to be a lot less likely to apply in the first place when they're really on the low end of the intelligence spectrum, okay? They're much more likely to be up on the higher end. Colleges are full of nice, bright people like you. So it causes a skew in the distribution, okay? Now again, positive and negative are not value judgments at all, okay? It sounds like a good thing to be on the, that you're a member of a negatively skewed distribution. It's not a bad thing, okay? And so it's not a value judgment. Now, so the reason why I think some people find this kind of counterintuitive is that we're kind of emphasizing where most people fall. Most people are under these two peaks, okay? And to call this one positive, meaning, the hump is not on the positive side, it's kind of towards the negative side of things, all right? And, for a negative distribution, the hump is over towards the positive numbers, not the negative ones. So don't think about where the hump is. The hump doesn't dictate whether it's positive or negative. It's where the tail is being pulled. Okay, so you kind of picture a little guy here pulling this distribution off in the positive direction. Okay, the slow grandpa types that are really slow to respond in milliseconds. Okay, they're pulling that distribution off in a positive direction. On the other hand, a few Forrest Gumps do get into college, all right, and they pull the distribution off into a negative direction, okay? So think of that. That's your way to remember positive and negative distribution. It's not where the humps are, it's where the tails are being pulled, okay? All right, so that's skew. And like kurtosis, there are mathematical expressions of skew, and we're not going to go there in terms of calculating those. All right, so it can be mathematically expressed, but we're just going to keep it as a conceptual thing for us. All right, so a normal distribution can become skewed. It can become kurtotic. Is that a word? Kurtotic. All right, those are the two ways that we can mess with normal distributions. Okay, now not everything's normally distributed. So sometimes we see what are called bimodal distributions. Now, this is a very extreme example that I'm going to give you here, but it's bimodal. In our next lesson, we're going to learn about measures of central tendency, and one of the measures is a preview that we're going to learn about is the mode. The mode is the most frequent occurring score or value in a distribution. Okay. Now, as you can see, remember the peak tells you, where most people are. So if these are pretend these are equally high here, that means there's a peak of people under this peak, and there's a peak of people under this peak. So hence it's bimodal. There's two mode values here. So this is maybe in a very extreme example, weights for males and females. Now it's nowhere near this neatly distributed, but most women tend to be lighter than males, and so males might be under this peak and females might be under this peak, but of course there's overlap in between and on both ends of it. Okay, so that is a nice picture of a truly bimodal distribution. All right, it's conceivable that you have 3 modes, 4 modes. It could be trimodal, quadrimodal. At some point, you just stop calling it by their specific names, and you would just call it multimodal. And at some extreme point, there's so many frequently occurring scores that it just becomes irrelevant to think about how many modes there are. Okay, at the extreme, think of a deck of cards. Okay, a deck of cards has an equal number of every type of card, and so it's flat, it's rectangular. All right. So if everything occurs equally as many times, we don't talk about the mode. You just say it's irrelevant. It's not applicable. All right. So, all right. Now, a computer will be very dutiful. SPSS, Microsoft Excel, will be very dutiful in telling you what the mode is when you ask for it. So by my way of looking at this, it appears to me that this hump is just, a millimeter or more taller than that other one. So let's just pretend now that it is. Let's pretend this one is actually a little bit higher. All right. So technically, this value underneath that peak would be the mode of this distribution. All right. So again, a computer is going to be very dutiful and tell you, you got one mode, and there it is. All right. So this is why it's very important to look at distributions of data. It's very important to look at your data. What if you hadn't seen this picture? What if you hadn't seen it and all you relied on was the computer to tell you very dutifully what's the mode? Oh, it's this many pounds. Okay. You'd miss the big picture that, wow, there's another big peak over here. So I always say, look at your data, look at the distribution of it. Okay, your visual system will see things that that the rest of your brain won't see. Okay, the rest of the computer won't be able to see. So multimodal distributions. Okay, bimodal is the most frequent, of course, but you can see trimodal, you can see multimodal. All right, good. Enough for now. Now, there's infinite number of other shapes. I'm only going to talk about a few. All right, I already mentioned rectangular. So a deck of cards is going to be a flat rectangle. I'm not going to bother drawing a picture of a flat rectangle. All right, there's 4 of each kind of card. For each suit in a deck of cards. If you were to plot how frequently each of them occur, 4, 4, 4, 4, 4, all 13 of them occur 14 times. All right, are you going to report that there's 13 modes? That's pointless. So it's it's just rectangular. I can't think of any good psychology examples of variables that are rectangularly distributed. So I'm just throwing out a couple that I can, if you were going to plot how frequent certain numbers occur in things like social security numbers, which are relatively random. Well, there's an underlying code in there, but or phone numbers. Okay, and of course we have area codes and those three number prefixes and whatnot. They mean, anyway, they're not truly random, but the occurrence of individual digits at any one place. Okay, you can have a 0 through a 9 at any one place in a social security number or a phone number. And if you were to plot how frequently 0 through 9 occurs in the third position of a phone number, for example, it's pretty random. It's pretty rectangularly distributed in a big population of phone numbers or social security numbers. So again, kind of a so what example. They're out there. Maybe not so much in psychology, but anyway, rectangular. Let's move on. All right, a couple other interesting ones are U-shaped and inverted U-shapes. Okay, so a U-shaped, an example of something that's U-shaped distribution will be income versus free time. And hold on, I'll show you an example of that in just a second. Okay, you could turn that U upside down and call it an inverted U shape, and it's kind of like a normal distribution, but not so not so sloping outward of the tail. So a true U shape, okay. So an upside down or inverted U shape. So I'll show you a couple examples of that in a second. Okay, and that's where I'm going to stop giving examples. All right. So there's an infinite number of other shapes. All right. They can be all kinds of whatever crazy shape. All right. So let me give you those examples here. So the amount of free time that people have and their income, the relationship between those two variables tends to be U-shaped in the population. Okay, so such that the less income you have, low income on this end, high income on that end, low free time on this end, high free time on that end. If you don't have much income, you're not maybe working so much. And no money, no job, lots of free time. Okay, so that's you. Haha. Guessing you don't have much much income, all right? Maybe you work a lot. I don't know. Sorry if I'm. So anyway, most college students are down here. You know, not much if any income and lots of free time. No excuses for not getting this work done. Yeah, yeah. All right. So someday you get a job. The more you make, someday you enter into the middle class. All right. So this is where your parents are in the middle class here, working all the time for the middle bucks. All right. No free time. Okay. Me sitting here in my office at nearly 9 o'clock. Okay, working, no free time. All right, middle income. And up at this end we have, well, Paris Hilton. Okay, tons of income, lots of money, nothing but free time. All right, so a nice example of a U-shaped distribution. Okay, here's a less fun one. So, in fact, a downright morbid one. So here's risk of death as a function of body weight. All right, so we have body mass index down here, and so a low body mass index means thin, skinny, middle, and obese. All right, and the absolute risk of death over here on this scale. So if you're too thin, that carries actual inherent risks. Okay, that's not healthy to be too thin. All right, especially when you get older. All right, we're finding that yeah, it's a little better to have a little chunkiness. Okay, especially when you get old. All right, your risk of death goes down if you're middle income, middle body mass. All right, okay, and then it rises again with obesity. All right, obviously. Okay, so nice example of a U-shaped distribution. All right, okay. Flip it around and we have an inverted U shape. So the classic good psychology example is something called the Yerkes-Dodson law. I don't like calling things like this a law. I don't think it's lawful, but it's sometimes called the Yerkes-Dodson principle. I like that name better. All right, so if you talk about arousal, stress, motivation, those kinds of terms. Okay, emotional arousal from low to high, and performance, however you want to measure performance on a test, performance on a stage, athletic performance, performance wherever. Okay, so from poor to good. All right, so if you're under aroused, you're going to likely have poor performance. You don't set world records, waking up from a nap with nobody to watch you and observe you. Okay, that's not when you're going to set a world record on something. Okay, so you need some, you're not going to perform well on a test if you just don't get at all aroused or motivated to study for it. Okay, you got to have an increased amount of emotional arousal, and your performance will rise, and hopefully you reach a peak here. So the goal, of course, is the peak of this distribution, maximum performance for the moderate amount of arousal, just enough to get peak performance. But of course, if you get too aroused, you start to choke and performance drops. Okay, I like this depiction of it. This was a more fun way to look at it, but I didn't want to show you this one because what's wrong with this picture? All right, well, it's showing it as a normal distribution instead of the U shape. It should be a inverted U-shaped distribution, not normally as this picture that I found drew it as. Okay, but anyway, yeah, if you're sleeping, you're not performing so high. Optimal performance for whatever the task is with a moderate amount of stress or emotional arousal or motivation, whatever term you want to put down here, similar terms. Okay, it's too much and you have anxiety, disorganization, high stress, you completely fall apart, and performance absolutely is as poor as it is over on the other end. Okay, so again, I like this cartoon, but it should be truly inverted U-shape, not normally distributed. That doesn't gently slope out like that. Okay, so that's just a handful of distributions, and most important terms in here were the concepts of kurtosis and skew. But I just wanted to begin to get you to think about how data is distributed. We're going to start looking at numbers. We're going to churn out some numbers and crank out some formulas and do some calculations. Yeah, I know. We're going to start using this guy a little bit, all right? And so we're going to be looking at numbers a lot more. And sometimes you can get lost, you lose the concept, all right? So like I was saying about bimodal or any of these, seeing how seeing how your data is distributed is utterly important, okay? And way too often people rely on the computer, Okay, churn out those numbers, get those means and standard deviations and modes and all that kind of junk computed by the computer, and never look at their data until maybe, well, ever, or well, it's too late. Okay, and miss the big picture that's right there when you see it. Okay, I think all those examples I went through are nice, visually clear examples. All right, kind of one it would be, you can recognize it would be a lot less satisfying to talk about in terms of just numbers. Think of that Hans Rosling video that I chased you off to watch, The Joy of Statistics. Okay, how awesome were all those sometimes complicated points he was making when you got to see the data move and you got to see it visually and graphically. Okay, we need our graphs, hence the presentation we had recently. Okay, remember, ugly graphs, don't make them. Okay, so thanks for your attention, and a little shorter than most of the recent presentations, so hope you enjoyed it. See you next time.